In physics, we recognize that there are three types of collisions. Okay, the first of those types is called perfectly inelastic. In a perfectly inelastic collision, the objects stick together after the collision. Okay, now the situation may be completely mundane. It may occur mechanically, for example, with these carts. Now with this cart here, I've got a nail. I'm going to place it like so. And then with this cart here, I have a close clip. And then what I'm going to do is line up the two carts like this and then collide them together like so. And then the objects stick together after the collision. That type of a collision is perfectly inelastic. Something a little bit more exotic, however, would be, say, nuclear fusion. With nuclear fusion, you have protons and neutrons which come together to form heavier nuclei. That's another type of perfectly inelastic collision. Okay, then secondly, we have what's just referred to as an inelastic collision. In an inelastic collision, the objects bounce off of each other. It's also a realistic situation in the following sense. During the interaction that occurs between these two carts as they bounce off of each other, like so, there are forces of friction that occur between the two carts. This causes some of the energy of the carts to be lost as heat. Some of that energy, by the way, takes the form of a sound wave. For example, after all, you could ultimately hear the collision when I do something like this. So where did the energy from that sound wave come from? Well, it came from the initial kinetic energy of the carts. So then therefore, because there is a little bit of heat loss, this then means that the total amount of kinetic energy of the carts before the collision is a little bit greater than the total amount of kinetic energy of the carts after the collision, because some of the energy is lost as heat during the collision itself. So it's a realistic situation. It's realistic in that energy is lost as heat during the collision. However, a little bit easier to picture mathematically is the third type of collision, which is called elastic. In an elastic collision, we assume that the time of the interaction between the objects as they bounce off of each other is minimal. This then means that the amount of energy that's lost as heat during the collision itself can be considered to be negligible. As we'll see, this is a perfectly reasonable assumption to make as long as the time of the interaction is short. So then therefore, for example, as these carts collide together like so, the time that they're interacting with each other is just a few hundredths or maybe a few thousandths of a second. So the amount of energy that's lost as heat during that interaction is quite small. What this then allows us to do mathematically is assume that the total kinetic energy of the carts before the collision is the same as the total kinetic energy of the carts after the collision. So then therefore the elastic collision is an approximation. So third, we have the elastic collision. Depending upon the textbook, by the way, sometimes it's referred to as the perfectly elastic collision. It means the same thing. During the elastic collision, the objects bounce off each other, but we once again consider the heat loss to be negligible. So the objects bounce off of each other, but we consider the heat loss to be negligible. As we'll see with an example later on when we get to the elastic collision, this is a perfectly valid assumption to make. Okay, now mathematically we begin by taking a look at a couple of situations involving the perfectly inelastic collision. We take a look at a one-dimensional case, and we also take a look later on at a two-dimensional case. With respect to the one-dimensional case, during this lecture I'll do a problem associated with the perfectly inelastic collision. We'll also take a look at a mini-lab exercise a little bit later on as well for the one-dimensional perfectly inelastic collision. Okay, let me go ahead and do some erasing here. And then let's go ahead and access our first problem here, this problem associated with the one-dimensional perfectly inelastic collision. I'm going to simulate the collision that is being described in this problem by using these carts. I do have to get a laboratory weight, however, in reference to the problem. So hang on a moment. Okay, let me go ahead and read the problem to you, copy it down into your notes as well. Okay, two objects undergo a perfectly inelastic collision in one dimension. The first object has a mass of 1 kilogram and an initial speed of 1 meter per second when it collides with the second object of mass 2 kilograms, which is initially at rest. So here's how I'm going to simulate this by using my carts. So this right here will be the first object with a mass of 1 kilogram. This right here, with the laboratory weight, will be a mass of 2 kilograms. This object here is initially at rest. Okay, and then this object here is initially moving in this direction at 1 meter per second. It then collides in a perfectly inelastic collision with the second object such that the two objects stick together, like so. Let me try that again. Gotta get them to stick. There we go, like so. And then after the collision, the objects then move in this direction with a final velocity, which we're going to calculate. And we're also going to calculate how much heat is lost during the collision itself. Now here's how we begin to set this up. So right here is the first object, M1 we'll say, with a mass of 1 kilogram, initially moving like so, with an initial velocity we'll call V1 naught equal to 1 meter per second. Okay, here's the second object, mass M2, this is 2 kilograms. This object is initially at rest, so V2 naught is equal to 0. And then the two objects collide and stick together as you saw, and they then have a common final velocity. So here are the two objects now, M1 and M2, moving in this direction with a final velocity which we'll call V final. What we're asked to do in part A of the problem is calculate that value, and then in part B we'll calculate the heat loss. During the perfectly inelastic collision, friction is the force that's causing everything to stick together. This then causes energy to be lost as heat. Okay, now here's then how we begin or proceed. We have change in momentum of cart number 1 plus change in momentum of cart number 2 is equal to 0. This is a one-dimensional problem, so I don't have to use any vector notation. And now I'm going to go ahead and write these momentum vectors, P as mass times velocity. So first of all, the first object. After the collision, its final momentum is M1 times V final. And then minus its initial momentum, which is M1 times V1 naught. And then we have the second object. After the collision, its final momentum is M2 times the same V final. And then minus its initial momentum, which is 0, because that object begins at rest, like so. And now the only unknown that's present here in the problem is the final velocity, V final, which we'll now go ahead and solve for. So let's do a couple of basic algebraic steps. So here are my steps. I'm going to first of all take this quantity here and move it to the other side of the expression. So when I do, it becomes positive, like so. And then with the two terms that remain, here and here, let me go ahead and add them together. When I do, the V final is common to both of the terms, so then therefore I could factor it out. When I add the stuff together then that's left, here's what I obtain, like so. So here's how you read this expression. This right here is the total amount of motion before the collision. This right here is the total amount of motion after the collision. And now the only unknown that we have present here is V final, which we can now solve for. So let's go ahead and divide the parentheses here to the other side and get V final by itself. Like so, and now we plug in our numbers. So here's what the numbers look like. 1 times 1, and then divided by 1 plus 2. This is a total then of 1/3 meter per second, which is the same thing in decimal form as 0.33 meters per second. And then lastly, we can now calculate the amount of heat that is lost by calculating the kinetic energy of the system before the collision and calculating the kinetic energy of the system after the collision. As we'll see, there's a slight difference between the two, and the difference is equal to the energy that's lost as heat. So here's then how we'll do part B. We'll do this on the lower board. Okay, so let's calculate first of all the initial kinetic energy of the system. Okay, just to give it a name, I'm going to call it K0. Now keep in mind that cart number 1 was the only object that was moving before the collision. So then therefore the initial kinetic energy of the system is going to be 1/2 m1 times v1 naught squared. Let's just go ahead and calculate this number. Okay, so we have 1/2 times 1 kilogram for the mass and then multiplied by 1 squared, and this just ends up being equal to 0.5 joules of energy. And now, after the collision, let's calculate the final kinetic energy of the system. So the final kinetic energy of the system, I'll just call it K, is 1/2 times the total mass, remember the objects are stuck together, multiplied by the final speed squared. So now let's just go ahead and do the math. So 1/2 times a total of 3 kilograms, that's here in the parentheses, and then multiply by 0.33 squared. And I get a different number than I did earlier. In this case, it's about 0.16 joules, like so. So the difference between the two then, therefore, is the amount of energy that's lost as heat. So 0.5 minus 0.16, that ends up being about 0.34. So the difference is 0.34 joules. That's the amount of energy that's lost as heat during the collision. So in the perfectly inelastic collision, the force that causes the objects to stick together is the force of friction. This then causes heat loss. Okay, in the next video, we'll take a look at a brief two-dimensional case of the perfectly inelastic collision.